Hello students, we are dealing the chapter ray optics. We dealt some of the topics in my previous classes. Now today we will see the refraction through prism. A prism is drawn in the board. An optical prism is a device that consists of three refracting faces. Here we have AB, AC as well as BC, which are inclined at some angle. The two refracting faces shares one common edge. So, we will try to see the refraction through the given prism. Here a beam of light strikes at the surface AB at point P, makes an angle of incidence I with the normal, and it enters into the prism. Normally prism we are considering here as a glass prism whose refractive index is mu2, we can say. The refractive index of glass prism here is mu2 and the refractive index of rarer medium is mu1. Now, when this beam enters into the denser medium, it bends towards the normal according to the property of refraction. Then the bent beam strikes at the other surface AC, which makes an angle of incidence R2 with the normal, and when it emerges out, it makes an angle of incidence, angle of refraction, angle of emergence with the normal. Now, when we produce this incident beam and refracted beam, these two beams meets at a point making some angle. This angle is called deviation angle. That is, angle of deviation is that angle which is made between incident beam as well as emergent beam. Incident beam and emergent beam. So, here delta is the angle between incident beam and emergent beam. It represents to what extent the emergent beam bent compared to the incident beam when it emerges out from the prism. Now, we will try to see the relation between prism angle, deviation angle, angle of incidence and angle of emergence. In this case, let us consider the triangle APDQ. So, we have to find the relation between I, E, A and delta. Now, from the triangle APDQ, from quadrilateral APDQ, we have APD, angle APD is equal to AQD is equal to 90 degree. Therefore, angle A plus angle D will be equal to 180 degree. From the property of quadrilateral, the total sum of angle will be equal to 360 degree. Therefore, angle A plus angle D is equal to 180 degree. Let this as equation 1. Now, from triangle PDQ, we have angle R1 plus angle R2 plus angle D is equal to 180 degree. Let this as equation 2. Equating 1 and 2 gives R1 plus R2, that is angle R1 plus angle R2 will be equal to angle A. Let this as equation 3. Now, in triangle XPQ, the deviation angle will be equal to sum of interior opposite angles. Here angle delta acts as an exterior angle for the triangle XPQ. Therefore, the exterior angle deviation delta will be equal to sum of interior opposite angle. Let this angle be say Y and this angle as say theta. So, Y plus theta will be equal to delta. In triangle XPQ, the exterior angle delta will be equal to Y plus theta. Now, from the figure we can say angle I is equal to R1 plus Y and angle E is equal to theta plus R2. both are vertically opposite angles. So, let this as equation 4. Now, from the figure I will be equal to r1 plus y, or y is equal to I minus r1. Similarly, theta will be equal to E minus r2. Now, so we have delta is equal to y plus theta. Substitute the value of y and theta in equation 4, we get delta is equal to I minus r1 plus E minus r2. So, this further gives I plus E minus r1 plus r2 inside the bracket. So, we got delta is equal to I plus E minus bracket of r1 plus r2. Now, we know that angle A plus delta is equal to 180 degree, and also the value of D is 180 minus r1 plus r2. From equation 2 we have delta, from equation 2 we have angle D is equal to 180 minus r1 plus r2 bracket. Let this as equation 5. Now, from triangle, from quadrilateral APDQ, we have A plus angle D is equal to 180 degree, or angle D is equal to 180 minus angle A. Let this as equation 6. Now, equating 5 and 6 gives 180 minus angle A is equal to 180 minus r1 plus r2. So, here 180 get cancelled out, and finally you will get angle A is equal to r1 plus r2. Now, we got the value of A as r1 plus r2. Now, substitute the value of r1 plus r2 in the equation delta is equal to I plus E minus r1 plus r2. The equation becomes delta is equal to I plus E minus angle A, or on rearranging this we get delta plus A is equal to I plus E. So, this is the relation between deviation angle, prism angle, angle of incidence and angle of emergence. Now, when we draw a graph between the angle of deviation and angle of incidence, the structure of the graph will be like this. We have a graph here. So, graph has been drawn between incidence angle I and deviation angle delta. So, it is seen that as we increase the value of I, that is the angle of incidence, the deviation angle decreases. At a particular point, the deviation angle becomes minimum, at which angle I will be equal to angle of emergence. So, that means angle of incidence will be equal to angle of emergence. At that particular point, the deviation angle becomes minimum, and after that with further increase of angle of incidence, deviation angle increases. So, there is a point at which the deviation angle minimum, this angle is called angle of minimum deviation, at which I and E both are equal. So, angle of minimum deviation is that angle of deviation at which angle of incidence will be equal to angle of emergence. That is, when we draw a graph between deviation angle and incidence angle, it is seen that with the increase of incidence angle, deviation angle decreases. At a particular point, this deviation angle becomes minimum, at which angle of incidence will be equal to angle of emergence, and that particular angle at which I becomes equal to E is said to be as angle of minimum deviation. Now, we will try to find out the formula for angle of minimum deviation. Now, we will see the angle of minimum deviation. Angle of minimum deviation is that angle of a deviation at which I becomes equal to E. So, here we have delta plus A is equal to I plus E. This is what the relation we derived. So, for angle of minimum deviation, we have I is equal to E. So, in place of I, we can put E. So, we get delta plus A is equal to I plus I, or delta plus A is equal to 2I, or I is equal to delta minimum plus A divided by 2. So, this is the value of I. Now, we have to find the value of R. Now, we know that angle A is equal to R1 plus R2. Let this as equation 1. Now, we need to find the value of R1 in terms of A. So, at angle of minimum deviation, I is equal to E. Now, for the first surface, according to Snell's law, we have mu 2 divided by mu 1 is equal to sin I divided by sin R1. Let this as equation 2. And for second surface, ray is emerging out from the denser medium and it is entering into the rarer medium. So, here using Snell's law, we have mu 1 divided by mu 2 is equal to sin of R2 divided by sin of E. Now, reverse it, we get mu 2 by mu 1 is equal to sin E divided by sin R2. Let this as equation 3. Now, comparing equation 2 and 3 gives sin E divided by sin R2 is equal to sin I divided by sin of R1. Now, at angle of minimum deviation, we know that I is equal to E. So, in place of E, we can put I. Putting that equation gives sin I divided by sin R2 is equal to sin I divided by sin R1, or further this can be written as sin R2 is equal to sin R1 or R2 is equal to R1. Let it be named as R. So, we saw that at angle of minimum deviation I will be equal to E and the refracting angle R1 as well as R2 will also be equal, and I named this angle as R. Now, equation 1 becomes angle A is equal to R plus R, or R is equal to A by 2. Now, we need to find the refractive index in terms of angle of minimum deviation and the prism angle. So, from Snell's law, we have mu is equal to sin I divided by sin R. Here the value of I we already calculated, which is equal to angle of minimum deviation plus A divided by 2, and angle R is equal to angle A divided by 2. So, replacing the value of I with angle of minimum deviation plus A divided by 2 and R with angle of 2, then mu becomes sin delta minimum plus A divided by 2 by sin A by 2. So, this is the relation between angle of minimum deviation, prism angle and refractive index. Now, we will see the angle of maximum deviation. The graph which is shown here drawn between angle of deviation as well as angle of incidence. At a particular angle of incidence, when I will be equal to E, we are seeing that the deviation angle is minimum. Apart from this angle, we are finding that for two different values of angle of incidences, the deviation angles remains same. Under this condition, there is a particular angle of incidence at which the deviation angle becomes maximum. This angle of deviation is said to be as maximum deviation angle. Let us see under what condition the angle of deviation becomes maximum. From the figure, here also the beam of light is incidenting, makes an angle of incidence with the normal. When it enters into denser medium, it makes angle of refraction R1, that is it bends towards the normal, and when it strikes at the other surface, it makes an angle of incidence R2, and finally it emerges into the rarer medium. So, the deviation angle becomes maximum only when the emergent rays grazes over the surface. This can be possible only when the angle of incidence in the denser medium R2 is equal to critical angle. So, if R2 is equal to IC, then deviation angle becomes maximum. So, at this condition we have sin of IC will be equal to 1 by mu, or in place of IC we can write sin of R2 is equal to 1 by mu. In this way, the critical angle can be determined, that is R2 can be determined. After knowing R2, if we know the prism angle, using that prism angle and R2, R1 can be determined, and after knowing R1, I can be determined, from which we can able to know the deviation angle, under what condition of angle of incidence the angle of deviation can be maximum, that can be known. So, once again, here the deviation angle becomes maximum only when the beam of emergent ray grazes over the surface. It can be possible only when the beam which is emerging out from the denser medium makes an angle with the normal will be a critical angle. If the angle of incidence is equal to critical angle, then ray of refraction grazes over the surface. Under that condition, the angle of deviation will be maximum. Now, next we will see the thin angle prism. Here we have the formula mu equal to sin dm plus a divided by 2 divided by sin a by 2. For thin angle prism, we can write sin of dm plus a by 2 as dm plus a by 2, similarly sin a by 2 as a by 2. That is, for thin angle prism, we can write sin dm plus a by 2 equal to dm plus a by 2 and sin a by 2 as equal to a by 2. Now, substituting this value in equation 1 gives mu equal to dm plus a by 2 divided by a by 2. Now, 2 to get cancelled out, we have mu is equal to dm plus a divided by a. Cross multiplication and simplification of this expression gives mu a is equal to dm plus a, or dm is equal to mu a minus a. A can be taken common, we get finally dm is equal to mu minus 1 a. So, this is the formula for angle of minimum deviation for thin angle prism. Now, we will see the dispersion. Dispersion is nothing but it is the splitting of white light into its constituent colors when it enters into the prism. Here a white light is entered into the prism, it has been split into 7 colors. The extreme colors are violet and red as shown in the figure. Violet light produces deviation angle delta V and red light produces deviation angle delta R. So, the deviation angle depends upon refractive index of the prism and angle of the prism. Let this as angle A. Now, dispersion is nothing but difference in deviation produced between two colors. Here we took violet as well as red. So, dispersion in this case can be written as D is equal to dV minus dR. So, from the figure we see that deviation produced for violet light is more, and the deviation depends upon the refractive index depends upon the wavelength. We know that lambda V is less than lambda R, therefore, the refractive index for violet light is greater than refractive index of red light. Accordingly, the deviation angle for violet light is greater than deviation angle for red light, because it depends upon the refractive index. So, the deviation produced, the dispersion in this particular case is given by D is equal to delta V minus delta R. Now, put the values of delta V as well as delta R, we get the dispersion D is equal to the value of delta V you can write as mu V minus 1 A minus mu R minus 1 A. Here A can be taken common, so dispersion becomes, dispersion is equal to mu V minus mu R minus 1 and minus minus plus 1 and minus 1. Here we have A as common, that is mu E is there and then minus mu R and after that minus 1 and then minus minus plus 1. So, here plus 1 and minus 1 get cancelled out. So, we have the formula for dispersion as mu V minus mu R multiplied by the prism angle. So, the formula for dispersion is given by the refractive index of violet light minus the refractive index of red light in this particular case multiplied by the prism angle. Now, after this we will try to see the dispersive power. So, dispersive power is given by omega is equal to dispersion divided by mean deviation. So, in our particular case, dispersion can be written as delta V minus delta R divided by mean deviation, means the deviation produced by any color which lies at the center point of V and R. Probably we can take as violet light. Here the deviation for the mean color you can write as delta. So, this is the formula for dispersive power. Further elaboration of this expression gives the formula for delta V we already have here, which is equal to mu V minus 1 multiplied by A, and then delta R also we have mu R minus 1 A, and the formula for mean deviation is mu minus 1 A. So, this gives mu V minus mu R divided by mu minus 1, that is W is equal to, the dispersive power W is equal to mu V minus mu R divided by mu minus 1. So, this is the formula for dispersive power. Now, we will see the graph that varies the refractive index with the wavelength. When we draw a graph between wavelength and refractive index, we find that with the increase of wavelength the refractive index decreases. This expression is called Cauchy's dispersion formula, which is applicable for the case of dispersion. Next we will see the dispersion without deviation. Here two prisms are arranged opposite to each other. When a beam of a light enters in the first prism, it will splits the incident beam, that is it disperses the incident beam into its constituent colors. The extreme colors are shown here, red as well as violet. When these two rays enters into the second prism, it will again refracts through the last end of the second prism. After refraction, the refracted beam moves parallel to the incident beam, so that the deviation between the incident as well as emergent rays is 0. So, only dispersion is there, that means the total dispersion we have to find out here. Let us suppose D be the dispersion for first prism and D dash be the dispersion for second prism. And according to the diagram, the total deviation, that is delta plus delta dash is equal to 0, where delta is the deviation produced for first prism and delta dash is the deviation produced for the second prism. So, the net deviation produced in this case is equal to 0. Now, we know the formula for deviation. Deviation is equal to dispersion is equal to difference in deviation between two colors, that is mu V minus mu R multiplied by A. This is the dispersion produced by first prism, and D dash is equal to mu dash V minus mu dash R multiplied by A dash. This is the dispersion produced by second prism. So, total dispersion will be D plus D dash equal to mu V minus mu R bracket A plus mu dash V minus mu dash R bracket A dash. So, this is the total dispersion produced by this combination of prisms. Now, from the expression 1, we find that total deviation is equal to 0. So, the deviation produced by first prism is delta is equal to mu minus 1 A and deviation for second prism is given by delta dash is equal to mu minus 1 mu dash minus 1 a dash. Now the total deviation produced here is 0, that is delta plus delta dash is equal to 0, or we can say mu minus 1 a plus mu dash minus 1 a dash is equal to 0. Or from this expression we can find out the value of a dash and after that substitute in the equation 2. So from this equation 3 we have a dash is equal to minus mu minus 1 a divided by mu dash minus 1. Now substitute the value of a dash in expression 2, we get the total dispersion is equal to mu v minus mu r multiplied by a plus mu dash v minus mu dash r multiplied by a dash. The value of a dash is minus mu minus 1 bracket a divided by mu dash minus 1, or further this can be written as mu v minus mu r multiplied by a minus mu v dash minus mu dash r divided by mu dash minus 1 multiplied by mu minus 1 a. From this expression we can take mu v minus mu r multiplied by a, or a as common in this expression, which gives a, taking a as common we get mu v minus mu r bracket minus mu dash v minus mu dash r divided by mu dash minus 1 is actually dispersive power. You can write here as omega dash, where omega dash is the dispersive power of second prism. So after that we have mu minus 1 bracket close. Now multiply the first term on its numerator as well as denominator by mu minus 1. The expression gets a bracket mu v minus mu r divided by mu minus 1 multiplied by mu minus 1 and minus omega dash mu minus 1. Now after this we have mu minus 1 can be taken as a common factor. So take that mu minus 1 outside, a mu minus 1 under bracket mu v minus mu r divided by mu minus 1 minus omega dash, and we know that mu v minus mu r divided by mu minus 1 is nothing but it is the dispersive power of first prism. So it can be replaced with omega. The expression comes out to be a mu minus 1 omega minus omega dash, and we also know that a mu minus 1 is nothing but it is the deviation produced by first prism. So this can be written as the total dispersion d is equal to deviation multiplied by omega minus omega dash, or omega can also be taken outside. So this gives deviation is equal to delta omega 1 minus omega dash by omega. So this is the total dispersion produced when two prisms are arranged alternate to each other such that the bases are opposite to each other. So in this particular situation, a beam of a light when enters into the first prism, it splits into 7 colors, that is the beam disperses, and when it enters into second prism, the beam bends towards the base in such a way so that dispersion will be there, but there is no deviation, that is the emergent beam moves parallel with the incident beam. So these are the topics we saw on today class in the refraction of prism, and we will see the optical devices in our next class. Till then, do your level best and practice. Thank you.